Alright, hell yeah. This is the MIT Open Courseware Engineering Dynamics. Now this is the first problem. I'm just going to go over the fast solution, then we'll get into it. So we have a football that has a velocity at an angle. So it has an upward component and a sideways component. Sideways component's always the same. In this case, it's going to be 40 feet per second this way. So every second of hang time in the air, we're going to move 40 feet. Okay, so now this video is just about getting an intuition of what happens when like an object goes up. You do have gravity, has an acceleration. This acceleration term, what it says is it's changing its velocity. So this upward component, total is 80. I'm just going to say it's 64. It's really closer to 69, but 64 just divides by 32 so well. So what we're going to have is, after the first second, this velocity is going to go from 64 feet per second to 32. Cool. And then the next second, it's going to lose another 32 feet per second. It's going to go to 0. And then in the third second, it's going to pick up 32 feet per second and then pick up 64. So the bread and butter of this video is like, hey, my upward speed here is 64. And then my speed here is 32. So let's find the average. So I'm going to say the average speed between these is going, and that equation is going to be 64 plus 32 divided by 2. That's going to be 48. So right here I have an average speed of 48 feet per second, and I traveled for 1 second. So I know that this height has to be 48. So this video is just all about, hey, let's put in some coordinates on here. So we're 40 in the x and then 48 in the y. Same thing here. For this second, I have an upward speed of 32. I go to 0. My average speed is going to be 16 feet per second. I did that for 1 second. I must have gained 16 feet of height. So my coordinates here are 80, and then 48 plus 16 is 64. Okay, sweet. And then the same thing here. I lose, my average speed is it's 16 feet per second. It's just in the downward direction. And so if my average speed is 16 feet for that 1 second, I must have traveled 16 feet this way. So now we're 120 and back at 48. My average speed here between these is going to be 48 feet per second. You know what I mean? It's downward. I mean, so that's how, and that's the height we're going to lose. We're going to get back to here. So this video is also, you know what I mean, like, hell, let's find the coordinates of the grandstand. So the grandstands start at 55 in the x and then 0. Okay, so let's move over to 80, and we're going to move over 25, slots, and so I must go up 25. So this position is going to be 80 in the x and then 25. And I did have a typo in my problem, so let's do this next one. We're going to go, it was 25 to get to here, and then we're going to go another 40. So it's going to be a 65. So we're going to go 65 to here. So we must have a height of 65 in the grandstands. Our total height is 64, so I'm just going to write the grandstand height is 120 and then 65. I mistakenly called this 80 in the video, was not right. But the whole take-home point is like, cool, we have coordinates for the grandstands and we have coordinates for the projectile. The football can't be inside the grandstands, so so the football must have hit the grandstand somewhere between here and here. And you can just guesstimate. So that's what this process was. And the other thing is that for not the next part, but part 4. This is an equation, and so we're just going to actually get an equation for position for this this arc, and then an equation for position of this. Part 3 is similar, but we use kinematics. This is going to be broken up into 2 components, a y and an x, as a function of time, and then this will be the constraint. Alright, hell yeah. But that was the whole point of this video, is just like, well, can you have some intuition of actually just kind of plotting this? The first video was just, hey, I'm going to have 2 seconds of hang time up, my speed's going to be 0, my initial speed's going to be 32, and we just kind of did a linear approximation. And then we did know that a curve is parabolic, we just didn't do the extra step. In this video, we're kind of taking that extra step and actually plotting those points. But if you just said my speed is 64, at the top it's 0, and that's going to happen at 80, and then I'm going to go back down. You know what I mean? You're not too far off of where this thing's going to hit the grandstands. So that's kind of the whole point of these videos. Get an intuitive, you know, perspective on how to change your velocity. Why acceleration is change in velocity, and how you can use that to get change in position. Alright, so now for the video. Alright, hell yeah. So MIT has an open courseware. So this is engineering dynamics. This is the course that, hell yeah, let's try to do it. You know, I've already watched a bunch of lectures, so let's try to do the problems. Anyway, so each problem, this professor's pretty cool. It gives you a concept question. So the concept question in this, we have a football that's being kicked into these stands, is what's the magnitude of the horizontal velocity of this football at the top of the arc? And, you know what I mean, I don't know if it's a trick question, but it's the horizontal component that you start a projectile always stays the same. The reason that this upward velocity will like come to a 0 and then come back down to Earth and have a negative velocity is because its mass, and you have a huge Earth underneath you, and its gravity that's like, you know, you can almost think of it as like a magnetic attraction, or however you want to think of gravity, but those things are going to collide and come together because of those gravitational forces. But there is no, I like to think of it as there's no Earth sideways. You know, there's no Earth over here, and there's no Earth over here. So when you kick this football, the football's not, you know, traveling that direction, slowing down, because you have a big old chunk of mass out there. So yeah, it's kind of cool. Projectile, the velocity will always be the same. Now, you know what I mean, there's going to be air that's going to be dragging on any sort of object, but just in general, in an ideal sense, that horizontal component will maintain the same. Okay, hell yeah. So this video, I also want to go over, we'll see if we do the entire problem, but let's start with another way to kind of guess, you know, kind of guess the answer. And then we really can understand what's happening with this acceleration of gravity. So if we have acceleration of gravity, I'm just going to say, yeah, it's going to be negative 32. Cool. And I'm going to say that's feet per second per second. So I kind of simplified it, negative 32. Our velocity component is going to be 80 this way. So what I did is like, hey, well, what's twice 32? That's going to be 64, and that's going to be pretty close, because this upward component is going to be the cosine of 60. This is a good one to know from a decimal. I like to know things from decimals. This is 0.866. It's 86.6%. In a lot of guessing problems, I just call this 100%. At this point, you can just say, hey, look at this. Look at this arrow, and it's literally like almost the same size as this arrow. Now, if you go in this direction, hell no. You know what I mean? Like this arrow, if I split this 80, because that's like this arrow represents 80. This hypotenuse represents that number. And if I just split it in two, like, yeah, that's going to be the horizontal component. So even just visually, I can see this horizontal component's 40, but I also know, you know what I mean, you should know sine 30 is 0.5, and that also means that cosine 60 is 0.5. And let's do that because, you know, this involves trigonometry every time. So if we have a right triangle, and I always do a 30-degree triangle, it's kind of the easiest one. I do the sun is shining, so this is the sine component, and so we have sine of 30, that's going to be 0.5. And again, this is the hypotenuse. I would always take your hypotenuse and at least divide it in two and see if any of the others kind of match. Divide it in other segments and see if. But anyway, so yeah, you can see that this is half the hypotenuse. Now this is going to be pretty close to the entire hypotenuse. I don't know. Maybe even you can see that's 85%, but it's 0.866. Cool. And I guess what I draw this is because if we know the inside of a triangle has 180 degrees, and I just never think of that. I think like some concepts are just like, that seems like 8th grade, you know, middle school. So why do I even want to think about that? But kind of the pro move is to be like, well, you know, if you already know it's going to be a 90-degree triangle, so what's left is 90 degrees, and it has to be split between this 30 and whatever this one is, and so this becomes 60. And so, yeah, I'm trying to get better at doing the right triangles where, yeah, I'm always choosing, like, this angle is theta. Well, might as well choose this other angle as phi, you know what I mean? And then you kind of know that theta plus phi are going to equal 90, and you have a little equation there. So, anyway. All right, so, yeah, so what's 0.866, that percentage, or 86% of 80? And so I'm just going to run this in my calculator. 0.866 times 80. And we're a little bit higher. This is 69. But still, you know what I mean? Who cares? I'm just going to call it 64. It's kind of an easier number to work with. Especially because I'm just trying to learn what's going on with this component. What this says, and why I write, you know, gravity has units of, like, you know, feet per second squared, but I write it as feet per second and then divided by seconds, because this is going to spell it out. It's going to be a change in velocity of, so you can even write that out, change in velocity of feet per second per 1 second. You know what I mean? So if, and this is the change in time, but what I really like to do with problems, especially if I can just choose a change in time of 1 second, especially with these projectile problems. They're usually only in the air for like 5 to 10 seconds, and so that's what we have right here. Okay, so let's do it. So what does this mean? This means that because we have an Earth underneath us, we're going to have this football. Its velocity is going to change in this direction. So if it had 64 feet per second with an upward component, after 1 second we're going to have to subtract 32. So just mentally you're just like, oh, okay, hell yeah. So my velocity right here is 64. In 1 second my velocity is going to be 32, and then in another second my velocity is going to be 0. And then coming back down, my velocity is going to be 32. And let's write these in. Maybe you don't know where the positions are, but now my velocity coming down is 32, and then I'm going to hit the ground at 64. Okay, so we kind of have this picture, and what I'm going to do is kind of redraw this. And so let's talk about what happens. So if we have an upward velocity of 64, and we're going to travel for 1 second, at some point we're going to get to a position of, I'm sorry, our velocity is going to go from 64 to 32. Cool, so let's just stop there. That happened in 1 second. So we have 1 second, and our velocity was 64, now it's 32. So the bread and butter of kind of figuring out mentally what's going on is this right here. If I started with a velocity of 64, ended with a velocity of 32, even if you don't know if this is like a linear or gradual situation, you're just like, well, we took a short enough change in time. I mean, we're basically doing, you know, like the calculus, just in bigger chunks. So I can say, hey, my average velocity was going to be halfway between these. So the equation for that is add them up, 64 plus 32, divide by 2. So I'm going to do that. 64 plus 32 is 96. Sorry about that. Is 96. And then half of 96 is going to be 48. Alright, sweet. So I know my average velocity is 48 feet per second, and I know I did that for 1 second. So what this is giving me is my height right here. So now I know how high, after 1 second, I'm going to be 48 feet off the ground. And we can go back and be like, well, does that make mental sense? Yes, because I can't say I was going 64 feet per second for a height of 64 feet. And, because I'm slowing down. And I can't say I was going an average speed of 32 feet per second for that second and having a height of 32. It has to be somewhere in that middle. Okay, hell yeah. And now we can even get this direction too. So we're going to, we know our horizontal component is going to be 40 feet per second. And cool. And so that is going to be our average velocity. That is our velocity in this direction. It doesn't change. So that's going to be our average velocity at any chunk of time. So we went 40 feet per second for 1 second. So over here I'm going to be a distance of 40 feet. So this distance is 40 feet. Okay, so now I can actually get, a coordinate on here. We're going to say it's 40. Alright, hell yeah. So we have this coordinate, which is 40. In this direction, so this is kind of my x direction, and my y direction is my height. And so we're going to be 40, 48. Cool. So now we're just going to kind of plot these points. So now we have a upward velocity of 32. In the next second, because of gravity, our velocity is going to go to, and we know that these have to be basically the same. So we're just going to make a bunch of those. Every second, our horizontal component is going to be like that. We said this was 48 feet so far. And in another second, our velocity is going to be 0. So we're going to have 0 upward velocity. Our average velocity between these is going to be, well, we had a speed of 32, and we slowed down to 0. So our average speed is 16. And we did that for a second, so our height is going to be 16. So we're going to add from 48, so our height over here is 48 currently, plus 16 is 64. Okay, sweet. So this is going to be our top height. We're going to be at and we went another 1 second, so in this direction, with 40 feet per second, we're going to travel another 40 feet. So in this direction we're going to be 80, and we're going to have a height of 64. We have no upward velocity, and now gravity is going to change our velocity in the other direction to a positive 32, or I mean this negative 32. So we're going to have a 32 feet per second in this direction. We went from 0 to 32 feet per second. Our average velocity is 16, and we did that for a second. So now our height drops by 16. So 64 minus 16 is going to be is 48. You know what I mean? And obviously it's going to match over here. And our x direction is going to be now 120, and now we're going to be at a height of 48. Okay, sweet. Last one. So we have a downward speed of 32. In the next second, we're going to have a downward speed of 64. Our average speed is going to be 48 from this equation that we already solved for. And so our height is going to be reduced by 48. So our average speed, and again, let's do that same thing. Our speed here is 32 feet per second, and we're going to travel for a second. We're at a height of 48. So it's not going to be 48 minus 32, because we speed up. We speed up to a speed of 64. Now, we're not going to, in that second, we're not going to travel a distance of 64 feet, because, our average speed is somewhere in between these. And because we took a small chunk of time, hey, I'm just going to say it's halfway. Even though in this case, our speed does get reduced linearly, and so it gets every, per second, we're losing speed in a linear fashion. So our average speed is 100% halfway between 32 and 64, and that's 48. Cool. So now we have our average speed is 48 feet per second. We're going to do that for 1 second. That's going to give us our distance. And I'm not even using equation. I'm just saying. Alright, sorry about that. My camera cut out. Yeah, we're just using intuition. We're saying our average speed is 48 feet per second. I'm going to go for a second. I must have traveled 48 feet. But you can also go back and be like, what did we just do? Well, we took that average velocity in feet per second, multiplied it by seconds. Always pull out the units. I always say the units are the equation. And for sure, now we just have an equation for what we did. And so that's all I wanted to point out. All right, hell yeah. All right, hell yeah. So let's grab a new sheet of paper. Kind of now that we kind of know what we're looking at, we're going to have these increments of 40. And cool. And then we're going to go up to a height of 48. And then a total height of 64. So if this is 40, I guess this is 40. 40, 50, 60, 70. So cool. Our highest height is going to be 64. At this one, it's going to be 32. 1, 2, 3. No. This is going to be 48. After 1 second, our height's going to be 48. So it's going to be close to there. So this is where we get that kind of parabolic shape. Come over here, and we're going to be kind of mimicking it. Okay, so now this is where I wanted to, let's throw in these coordinates. This is 0, 0. This position is 40, so we have 40 here, 80, 120, 160. So this position is 40, 48. This is going to be over 80, but up 64. This is going to be over 120 and up 48. And this is going to be 160 but 0. Okay, now let's put in the grandstands. The grandstands are going to happen at 55 feet. So this is 55, and they're going to go upward at an angle of 45. So if we go over to 80, we would have to go 5 to 60 and then another 20. So we're going to go 25 here. We must have to go up 25. So this position of our grandstand right there is going to be over 80, up 25. Okay, now let's go over here to 120. It's 25 to 80 plus another 40. So we must go over 65 this direction, and then we're going to go up 65. So and just visually, we got this pretty much drawn to scale. So I'm going to be up here. So we have a distance of 120, and then, yeah, we're up 80. Cool. And so right there, we have what I wanted to do with this video. You know what I mean? This is, and if you don't see it, you know what I mean? Like, hey, the grandstands are higher than our position right here. And this comes up a lot. I'm just going to choose a graph of like x squared minus 6x plus 2. Let's see if that even crosses. Cool. So that crosses the x-axis. So let's do this. So if I have y equals x squared minus 6x plus 2, this gets into like the, hey, even if you don't know like the shape of something or everything about it, you know what I mean? Can we just know like 1 or 2 points and then see if that builds on the solution? Because I guess what I'm saying like right here is that this thing, it can't be below the grandstands. It must have hit the grandstands a little bit sooner, so it must have hit somewhere like right in there. So now I just know that where it hit the grandstands is less than 120 feet, and maybe it's 110, and that was from part 1. We were pretty much able to, sorry, I'm washing clothes and I just have to, so sorry if it's noisy. Anyway, but hell yeah, so I use this method of like the 0, 1, 2. This is kind of cool. Let's just throw in 0. So if I throw in 0, y, and I don't know, I would just do that. Y of 0 is 2, so cool. Or just say y is equal to 2 when x is equal to 0. Cool, moving on. Now let's throw in 1. So we would have 1 minus 6 plus 2. So cool, that actually works, because if we throw in 1, we're going to get, what are we going to get? Well, I just said it, 1 minus 6, that's going to be minus 5 plus 2, we're going to get minus 3. Hopefully I did that right. So we get negative 3 when x is equal to 1. So we know, like, what does this give us? We know that there is a solution. So let's like even, I don't even know. Just visually, I just know that there's going to be a solution between, no, is that right at all? Yeah, no, that is right. Yeah, because when we throw in x, yeah, we get a positive, and then we get a negative. So let's say we had x equals to 0.5, and maybe y is 0. You know what I mean? So there you go. that's when it's going to cross the y-axis. If you want to chart this out, we're going to have x is equal to 0, y is equal to 2, so we're going to be right there. X is equal to 1, y is equal to -3. Cool, so this is kind of what we have right there. So hell yeah, x crosses. And then, I don't know, you know what I mean? If you throw in 2, you're going to get 4 minus 12. Well, you're still going to get negatives. So, I don't know. This technique might be the 0, 1, 2, 10, just depending. Because now let's throw in 10. We're going to get 100 minus 60 plus 2. Cool. So we're going to get 42. All right, so when we throw in x is equal, and I should have wrote these the other way. I should have put x out. But anyway, if we throw in x is equal to 10, y is equal to 42. So now let's go back to, hey, we're going in the positive. X is 0, x is 1, x is 10. That's why I wanted to rearrange these columns. But y is equal to 42. So here we went from a negative to a positive. So hell yeah. So let's do that. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And hell yeah, our y value is way up there. So somehow we had to get from here all the way up to there. You know what I mean? So we must cross the x-axis somewhere. So hell yeah. There must be a point where x is equal to maybe 5, that y is equal to 0. You know what I mean? So let's throw that in. So we have 25 minus 30 plus 2. Hey, that's pretty close. You know what I mean? So that's kind of that kind of sums up, like, and I just don't think people spend time like undershooting and overshooting. You know what I mean? It's just like, hey, I know something about this, and so that's kind of what we're doing. That's exactly what we did. We got this point, and then we're just like, well, I can. And then what this does is it shows you that this grandstand is an equation. You know what I mean? So we can have an equation for the grandstand, y of g of x, and then we can have an equation of the parabolic arc, of the projectile, and this is going to be y. You know what I mean? It's still a yx, and I guess yeah, that's of the projectile. But now we can see that maybe when these two equations, equal each other, maybe that point's going to happen right here. And so there you go. But that might be the harder part. You know what I mean? This is like maybe the magic trick. Like I don't know even how to make this line. All right, hell yeah. So this is tripping me out because when you do projectile equations, you usually have y is equal to like 1/2 acceleration t squared. We have the kinematic equations, plus velocity initial t plus initial position. This is our equation for, y in the vertical direction, and usually x is, acceleration is 0, but it can still have an initial velocity, so it still might be v naught t plus x naught. You know what I mean? And these are going to be in the x direction, these are going to be in the y direction. But still, this is just the y component and the x component, where it's just like, well, isn't this actually a geometric line in space? Yeah, this would be, the equation for this would be y as a function of x. It would be something x, probably squared. But this generic form, this would give us the actual position of that football. And it's just fascinating that I don't take the time to go back and get that equation, even though, like, when these are separate, they're very useful and I know how to use them. But for this problem, though, we do know in space where those grandstands are. And then we can say, hey, this is just a snapshot of space. We can get this arc of the football just as a function of this distance in the x direction. And so I think I'm going to do that for part 3, because that's more fascinating to me than, maybe that's going to be part 4. So I think the next step is just to solve the problem using the kinematic equations and then saying this is a line. And, this is an equation in its own right, and then it's going to be a constraint where, you know, I mean, if this passes this, well, it couldn't. It had to hit the grandstand somewhere. And so that's going to be our constraint. This y and this x. This x and this y will be like this x and this y are every point on here, but as a function of time. So when those equal the xy of this, because this equation, you know, just to spell it out, is y is equal to a slope of x, but then it hits down here at negative 55. So that's our equation. And so what you do is you take this kinematic equation for x, throw it in there, this into y, throw it in there, and your variable is time. So you solve for that. But yeah, so it's just, so we're going to do that next, and then we'll do part 4, where it's just like, well, let's just get an equation as a function of distance, and then just solve those two. You know what I mean? Because that seems like it would be mentally exactly what you'd be doing. This, it seems a little bit harder to see that constraint. All right, so thanks for joining me on this one, and hell yeah.